So this is our second lecture in Unit 4. So in last lecture we have seen that every rotation in a plane is represented by a rotation matrix, and moreover we have also seen that that matrix is an orthogonal matrix, correct? So now in this lecture we will see the Eulerian angle. It is very interesting topic. Before that, one should know what is a rigid body, and also first I will give you some information about a rigid body. Like basically, what is a rigid body? So wait a second. Yeah, so a rigid body is a system of particles in which the distance between any two particles remains fixed throughout the motion. Generally, rigid bodies are the bodies who don't change their shape and all during a motion. Not all bodies maintain their shape, but there are bodies which maintain their shape during a motion. Why do they maintain their shape? Because distance between any two points in that body is not changed during a motion. Hence, that body remains does not change its shape during a motion. I hope I'm clear. Not and even it does not changes its size during a motion. So this is a rigid body. This is very basic concept that we have studied in 12th physics. Then after studying about rigid body, we should also know that what are degrees of freedom. This is also basic. So degree of freedom is the minimum number of independent coordinates which are required to describe the motion of the system completely without violating the constraints. Like the minimum number of independent coordinates for a rigid body, the minimum number of independent coordinates which are required to describe the motion of a system are six, because there are two types of motion. Translational motion. There are two types of motion. Number first is translational motion, and the other one is rotational motion. And rotational motion. So basically, rotational motion and there are three coordinates which will help in the translational motion, and there are three coordinates which will help in the rotational motion. Fine. So now in our study we are studying rotation. That's why in the last lecture I have already explained the rotation in two dimensional, because in this lecture we will use all the concepts we have studied yesterday. So before proceeding, I would we are studying a motion of a rigid body with a point fixed. For suppose this is a rigid body and it is a fixed point. Suppose the fixed point is origin. So if origin is fixed, then obviously we cannot do the translational motion. Translational motion means um, see, translational motion means the motion along x-axis or along z-axis or along y-axis. These are the translational motions. Okay. So rotational motion, you know what is rotational motion? Rotational motion is Rotational motion is the rotational motion that you know generally in which we rotate a body. So in this lecture, we are considering all the rotational motions and we are neglecting the translational motion. That means a rigid body cannot take the cannot translate, cannot move in the x direction like this way or upwards or along the y direction, because this point over here is fixed. Am I clear? So we will consider only which type of motion, like this point is fixed. So we will consider only which type of motion, the rotational motion. That means the body can rotate. But you have to imagine all these things, because my laptop or your page is a 2D two dimensional image. It's a plane, it's not a three dimensional image. So to see all these things you have to imagine a rigid body, you have to imagine x axis, to imagine z axis, and this y axis is actually coming out of the screen. right? This x-axis, this is y-axis, and this you have to imagine that it is coming out of the screen. Okay, so now I was saying that we will consider the rotational motion of rigid body. So for our thing, the degree of freedom would be 3, because for a rigid body the total degrees of freedom are 6, but we are not considering translational motion. So we this will become the constraint. So we have to minus 3, and we have to consider 6 minus 3 degrees of freedom, that is the 3 degrees of freedom. Hence we have now I have explained that a rigid body with one point fixed has 3 degrees of freedom, and hence 3 generalized coordinates for its description. So will consider 3 coordinates in order to describe the rotational motion of a rigid body. So to describe the orientation of a rigid body about a fixed point, we use a metric of rotation that we have seen in the previous lecture. Is that clear? So now, before also telling, like proceeding, one should always know that every rigid body, like it has its own body axis. There are two types of axis. Basically, the plane, not the plane. Basically, the axis which we consider, like in which the body is, that is the space. For suppose generally we know how we consider x y z axis in a three dimensional space. This is, see the red line you can see, this is the x axis, this is y axis, and this is z axis. This is the general space, but every body also possesses its three coordinates, right? Actually the rigid body will possess six coordinates, but we cannot even imagine six coordinates. But in case when we are considering only rotational motion, that is we are considering a point fixed, in that case there are only 3 degrees of freedom. So we have three independent coordinates. Every rigid body with one point fixed will have three independent coordinates. That means there would be three axes of that body. This is called as the body axis. This is called as the body axis of the body. For suppose I have considered, I have this body, you can see this box type thing. So this will also contain its own axis. See the green line, you can see this green line is the x dash axis. The green line over here is the y dash axis, and the green line over there is the z dash axis. Basically these green arrows, they represent the body axis, and these red arrows are the axis of the space, correct? So there is always a possibility of like aligning both the axes. It is very simple. See, are you like observing this blue arrow thing? You just move it, in an anti-clockwise direction, and then you will observe, you can rotate it. See, this z-axis can get aligned to z dash. In the similar pattern, this x will get aligned to x dash, and this y will get aligned to y dash, and both body axis and the axis like of the space will can get aligned. So this is the basic. I know gets difficult to understand in an online lecture, but I think I'm making it quite clear. So this is a rigid body. It has its own axis. That axis is called as body axis, and the axis of the space is has been represented by these red arrows. Okay, now we have seen what is a rigid body. It has generally 6 degrees of freedom, but where three are for translational motion and three are for rotational motion. But now we are considering a body with a fixed point, that is origin is fixed, that is it is not able to do translational motions. That's why we will consider only rotational motions. Therefore the degree of freedom for such a rigid body which with one point fixed would be 3, correct? So I hope I'm clear. I have not even started with the main lecture, which is the Eulerian angles. So now I will proceed. See, these are the images of your notes. This is the basic that I have already taught. Go and read it. Like you'll get to know. And this is the theorem that we need to study now. See, what does it say? Define the Eulerian angles, obtain the matrix of. See, I've told you, some people called it Euler, some call it Euler, but for me it is Euler because even the spelling of Europe is like EUROP, but we don't call it Europe, right? That's why I call it Euler. So if you prefer calling it Eulerian, you can call it like that also. Some people call it Euler, and some call the name of the scientist as Euler. So it's completely your choice. Huh. So the theorem, see, what does the theorem say? It says define Eulerian angles. So now I will teach you what Eulerian angles are. After that, what is it saying? That obtain the motion of transformation from space coordinates to the body coordinates in terms of the Eulerian angle. So what is it saying? That obtain a matrix of transformation from the space coordinates to body coordinates. See, as I have already told you, that it is possible to align both the coordinates, but obviously this alignment means nothing but a transformation of the axis, correct? So if there is transformation, there would be definitely a matrix which would be responsible for such a transformation. Like in the previous lecture, we have seen that in two dimensional, but now everything is three dimensional. So now we will definitely get a matrix that will transform the body, like the space coordinates to the body coordinates. Like this x axis will get aligned to x dash, this z will get aligned to z dash, and this y will get aligned to y dash. Okay, in this concept we need to use the Eulerian angles. Okay, so the theorem says that which matrix is, like, find out the matrix, okay, that will transform such coordinates of the body in terms of, okay, in terms of the Eulerian angle. Now what is it saying? Prove further what? Yeah. Prove further that this matrix is orthogonal. Moreover, they are asking us to show that once you have find out the matrix, let us know that this matrix is orthogonal as well. After doing that, they are saying to deduce the matrix of inverse transformation from the body set of axis to space set of axis. So then they are asking for that inverse matrix also. Yeah, we'll do it, not a problem. So what are Eulerian angles? Again, I will go back to what I have like prepared to explain it to you. Wait a moment. Yeah. So rigid body I have already explained. So basically, what is Euler's theorem? This is Euler's theorem that says that we need six independent or generalized coordinate to describe the motion of a rigid body. Why? Because it has 6 degrees of freedom. Out of this six independent or generalized coordinates, three coordinates contribute to the translational motion and three coordinates contribute to the rotational motion. ठीक है, so these are three types of angles. Precession angle, which is represented by phi, then there is nutation angle, which is represented by theta, and then there is spin or body angle, which is represented by psi. Is that clear? See, now what we are doing is we will study the Eulerian angle. Now you have to imagine everything. Things are really interesting, but these online lectures are making it quite boring. But no, you can still keep on trying. See, Euler's angle. There are three types of Euler's angle. First is the precession angle. So first I will describe the precession angle. This precession angle is also called as, see, I have written over here, first rotation. What is it? The first rotation. During the first rotation, um, see, what are we basically doing? We are basically aligning both the axes, the body axis as well as the axis of the space. So we have to align it. So such transformation, we need to find the matrix which is responsible for such a transformation. Okay. So basically, initially, see this in blue, we have this x-axis, this is the y-axis, and this is the z-axis. imagine this y-axis being at the right side, this z-axis is upwards, and this x-axis, imagine it coming out of your like page. So in this way you can imagine the three-dimensional space, right? So now over here we have three choices of rotation. I will choose, or we will choose the z-axis. What I will do, I will rotate, uh, do a rotation along the z-axis. Now in order to imagine this kind of rotation, no, you have to see this. Wait, once a second. You have to imagine this kind of rotation. See, when I rotate along the z-axis, if I am saying the rotation has to be done along the z-axis, what you have to do is, you have to imagine this disk. I'm just showing this for you to understand more. See, this is z-axis, right? So now what you do is rotate this disk along the z-axis. Okay, so now when I will rotate, only this z-axis will remain at its own place. Only this x-axis and y-axis will change its motion in this form of disk. So this is called as, like, this is the disk rotating in the xy plane in this about the z-axis. The same thing you can do when you rotate along the y-axis. At that time your disk will rotate along the, like, rotate in the direction of the y, z and x axis. When you rotate along the y axis, all these things are really imaginary, but I hope this image is helping you to imagine well. So now proceeding, getting back to where we were. Wait a second, we'll get back to it. Yeah, so the first, yeah, over here, so the precession angle or the first rotation. So now what I am doing is, basically what we are doing, we are trying to find a transformation, such a transformation in which the xyz axis is getting aligned to a body axis, correct? That is the x dash, y dash and z dash, right? So initially we have the space, like the axis of this place, x axis, y axis and z axis. Now what you do, you rotate the z-axis. That means in the anti-clock, all the rotations are anti-clockwise. Okay, so you have to rotate. See, I have made this arrow that is in the anti-clockwise direction. Now when you are rotating z, so obviously z will be at its own place, and this x will be rotated, and it will change its position to x1 by an angle phi, because we are rotating with an angle phi. And similarly this y will also rotate with an angle phi, and this will get the new uh, axis, that is y1 axis. So now our origin and x, like ox, if there, suppose here it is o, so OX will get changed to OX1 and OY will get changed to OI1. Remember, in the last lecture I have already discussed two types of rotations in two dimensional. One was the plane for sorry frame rotation, and the other was the coordinate rotation. So if you ignore the z axis and if you consider only the x axis and y axis, then it would be very helpful to understand that this is nothing but a frame rotation that we have studied in the previous lecture. So we have also seen that in frame rotation, which matrix is responsible. How do we find that matrix? I have already explained in the previous lecture. So yeah, I'm proceeding. In this way, this would be see, these are the unit, what we called is that ijk are the coordinates, unit coordinates. So it will change. So see, this I have already explained, this is nothing new. If you have seen my previous lecture, then I have explained the matrix which is responsible for the frame rotation. So this was the matrix which was responsible for the frame rotation. Okay, so there we had only this matrix, like two-dimensional matrix. I know. But there we considered rotation in 2D plane. Here we are considering in 3D plane. So the x and y axis are changing, right? But the z axis is remained at its place. That's why we have this third column and third row like this. Otherwise, this one, this matrix, the inner matrix 2 cross 2 is similar to the frame rotation that we have already studied. Correct? Like these things are very interesting. So I think it would be good if you pay attention. So see, now I have discussed the first angle, that is phi, which is called as the precession angle or the first rotation. See, now getting back to our notes because we need to like study that, right? So this is the first rotation. See what is it saying? First of all, the space set of axis is rotated about z axis. As I said, we will rotate it about z axis so that yz plane takes the new position y1 z1. Now the yz plane will take the new position. See, this is y. Here there is some mistake. How can yz plane will take new position? Z is remaining at its place. No, so y-axis is changing. So there is some mistake in your notes. Please check it out. So see, the y-x plane is changing and it is getting the new aligned position, that is y, not aligned, new position, that is y1 and x1. Okay, and the new axis would be x1, y1 and z1. See, this is x1, this is y1 and z1 is at its own place. And the transformation equations, this I have already explained. These are the transformation equations. Then this is the matrix and we have named this matrix as D. So remember the matrix, this matrix as D. Now the second rotation, I will again explain it to you in my handwritten notes. So where was I? Yeah. So now precession angle I have already explained it to you. See, now where are we? Observe clearly. Our x 0x, that is x axis, has been changed. All the coordinates has been changed. Now the new coordinates after this kind of transformation are x1, y1, and this z is not, z and z1 both are what, equal. So this z is nothing but our z1. Okay, so now there has been a transformation with the help of this kind of matrix. So this matrix has changed, like our x transformed, and the new set of transformation, after transformation the new set of coordinates are x1, then there is y1, and there is z1. Now see, x1 and y1 are changed but z1 is equal to z. It has been remained at its own position. So z1 is equal to z. Okay, so yeah, next, this I have discussed. Wait, yeah. So this one, the second rotation or the nutation angle theta. Now imagine this black lines, x-axis, y-axis, z-axis. This was initially before any kind of transformation. Now what we did, we had the first rotation, which by which we got the new coordinates. What were the new coordinates? X1, we had y1, and we had z1. How did we obtain? When we rotated the z-axis through an angle phi. So this angle was phi, this angle was phi. Correct. Now what we are doing, we are again like transforming the now obtained coordinates, that are x1, y1 and z1. Now there are two choices. Z choice has been removed, the rotation by an angle theta in now, but there are two choices. We will consider the x1 axis. See, there are two blue lines, so we have two choices, the x1 axis and the y. These, see, initially we had xyz, we rotated through and along z axis by an angle phi. So now we have transformed coordinates, that are x1, y1 and z1, right? So now you can just neglect the xyz for now and consider blue lines. Fine. This black line is equal to blue line. Why? Because in the previous we have rotated along the z-axis, so z-axis will remain at its own position. So see, here there is x1 axis, here there is y1 axis. These are the new axes that we will consider. Here there is z1 axis. Okay, now what we will do, we will again rotate, but with an angle, sorry, along z1 axis. See, when I am rotating along z1 axis, you have to imagine that y1 axis and the z1 axis will change. See, black lines you have to completely ignore, right? Like these xyz axis, but here you cannot ignore because this black line is also equal to blue line. So I am considering this axis. Now I am making it black. Wait, I will change my ink. Hmm. Yeah, I'll make it green. So see, which axis I am considering now? Which axis I am considering? This one. This one. Yeah, I'm considering this axis. So this is x, this is y, and this is z. Forget the black lines, okay? So now what I will do, I will rotate along the z axis. Now you will rotate means you will change the alignment of, you will change y1 and z1 because you're changing it along x1. So this will not move. You will rotate it, right? It's like a disc. This disc will rotate, and this, we are rotating through this angle. So now y1 will get transformed to y2 because we are rotating with an angle theta, and z1 will get transformed to z2. Fine. So now our we have another transformation in which the axes have been changed. Previously we had x1, y1 and z1. We rotated along the z1 axis. So this axis will not change its position, but which axis would change? Y1 axis and z1 axis. This axis would change. Now y1 axis will get aligned to y2 axis, and z1 axis will get transformed to y2 axis, and this z1 axis will get transformed to, so this z1 axis will get transformed to z2 axis. Am I clear? So now this kind of rotation is the second rotation, and we call it as the nutation angle theta. Am I clear? Now where have we reached? We have reached to a new coordinates, which are, wait a second, I will remove these circles. Yeah, now we have reached to a new system, which is x2. So our x2 axis, our y2 axis, and our z2 axis, x2, y2, z2. See these red lines you can see, and you have to consider this blue line. See, again I will make it green now. Oops. Yeah. So again I will make it green. This x1, this x2, and sorry, y2, and this z2, x1 y, sorry, x2, y2 and z2. So this is the axis we have obtained after after this kind of rotation by an angle theta. I hope I am clear. I know it is quite like not difficult to understand, but everything is quite imaginary because everything is happening in three-dimensional space. So I cannot show it in this screen. For understanding three-dimensional space, we have to imagine it. Or I would have made a video which was quite difficult to help you view a three-dimensional image view, but I hope it's clear. So initially what we did was, see, previously I am again repeating, what we did, what we had this xyz axis, we rotated through an angle theta, through an angle phi along z axis. So our new coordinates was z1, x1, y1, and then z1. In this way we had this new um, coordinates. So after obtaining these new coordinates, we again transformed by an angle theta, but this time I considered z1 axis. I took the rotation along z1 axis, so that the x1 axis, so that the x1 axis will remain at its position and the rotation would be in the y1 z1 plane. So now y1 z1 plane has transformed to y2 z2 plane. So in that space, what we got? We got x2, y2, z2, this kind of space. Now this is called as the second rotation or the nutation angle theta. Rotate rotation by an angle theta in counterclockwise direction about x1 axis. Again we can get all these matrices, because I have already told you that for every rotation we have a matrix. Here we everything is happening in three dimensional, so we have a 3 cross 3 matrix. Here x coordinate did not change, that's why we get the first column and the second column like that. And this is a 2 cross 2 matrix, inner matrix, which is responsible for the rotation which happened in the y1 z1 plane, and which made the y1 z1 plane to get transformed to y2 z2 plane, and this was rotated, the entire plane was rotated by an angle theta. Okay, now I'll again proceed to my third rotation, and this rotation is called a spin rotation or body angle, that is psi. So now here it is performed about z axis, okay, that is its own axis by an angle psi. See, now we have, I know everything is getting complicated, but now what you have to imagine, green also is already used. I'll have to change color again. This color, yellow color. I know it looks bad, but no option. So I'm using this color. Yeah. So see, now with which axis we will consider initially? I will consider this y2 axis and x2. So this red one is x2, I think. No, this is x3. This is x2, the blue one. And here I will consider the z2 axis, this one. Okay. So I know my drawing is really bad, but I hope. Yeah. So this is the axis I will consider. The y2, x2, and which one? The z2. Okay, now what we will do, I will again rotate this axis. Now along what? Along z2. See, here there is sign of rotation anti-clockwise. You are rotating z2. So z2 will not change its position. Z2 will be equal to what? Z3. After rotation, z2 will be z3. And this, and in see, here there is one more difference. You can see this z dash, y dash. See the y dash. I think this one has been written by mistake. It is y dash. And this x dash. What are these? Remember previously I have told you that we what we are actually doing. We are aligning. Actually, we are transforming the three-dimensional axis, that is the space axis, to the body axis. I have told you every body has its own axis. What we are doing, we are finding a matrix which actually transforms the space axis to the body axis. So this is the body axis. We are almost there. See, we have reached to this yellow line, but we have actually not aligned. We started from this black line. See, now I need this black line. See, x-axis, y-axis, and z-axis. From here we started. What I did, I rotated it along this z-axis. So x came to x1, y came to y1 by an angle phi. Second time what I did was I rotated along this x1 axis. So this became x became x1, and finally we reached here. Now what I will do is I will again rotate along the z2 axis, sorry, the z1 axis, the z2 axis, and I will rotate along this, so z2 will be equal to z3. But this plane will change. Y2 will get transformed to y3, and x2 will get transformed to x3, right? So you can see these red lines. Now we have got this after transformation, which is obtained by rotating the z2 axis by an angle psi. But see clearly what we got. we got that our Z3 have reached to our Z dash position, our Y3 have reached to our Y dash positions, Y3 has reached to our Y dash position. See, this is Y dash, we have reached here, and my x3 has reached to the x dash position. What are these dashes? X dash, y dash, z dash. This was the body axis. See, we have aligned. Finally, we have reached our destination. From where did we start? We started from these black lines, x-axis, y-axis, and z-axis. After three rotation along different axes, that is after three times rotating, we have reached to a destination, that is we have transformed the x-axis, y-axis, z-axis to x dash, y dash, z dash. That was the body axis. And who helped us? Euler angle helped us to get there. There were first Euler angle phi, second Euler angle is theta, and the third Euler angle is psi. It has its own names, as I have already discussed. So I hope I am clear. This was the third rotation and it is called as the spin or the body angle. Okay. So now I know, I hope you're not getting bored. This is really interesting. I would like to suggest you to read more about it. So we have not completed the question yet. Where is the question? Yeah, here it is. See, second rotation. This is the second matrix which is responsible for the second rotation. Then we have the third matrix, matrix B, which is responsible for the third. See, here also there is Z1, Z2, Z3. We have reached to our position, isn't it? So after that, yeah. So now they are saying that okay, fine, you have three different kind of matrices. You have taken like three rotation, but they have asked in a question. They have asked in the question to find one matrix that is responsible for rotation. They are asking us that how did we which matrix helped us to transform this axis, x-axis directly to x dash, y-axis directly to y dash, and the z-axis directly to z dash. Now we collectively have written three rotations, we have made three matrices, but see what our question is. Our question is to tell or to find that one matrix which is responsible for such kind of transformation. Where is the question? Wait a second. See, the question is obtain the matrix of transformation from space coordinates to body coordinates in terms of Eulerian angles. So we need one matrix. So obviously we know that the composition functions. What are composition functions? First function we operate, then we get the the point from the range, that the next point becomes the domain next, or the range becomes the domain of the next function. I cannot explain this right here properly, but I know all of you know composition functions. In the same way, the product of three transformation matrices will give us the final result. Like if we have three matrices and we like a b c and we multiply all the three matrices, what we get, transformation obtained after after using a matrix and a transformation matrix A, we will get something. Then again operate B, then again operate C, and finally we will get a combined transformation. So that we have to obtain the combined transformation. See, in the last what we did, we used the B matrix and we got x dash. How did we get x dash? We get x dash by obtaining the by operating the matrix B on x2. But how did we got x2? See, again I will go back. How did we got x2? We got x2 by operating the matrix C on x1. See, how did we got x2? We got x2 by operating matrix C on x1. But how did we get x1? We have already done. We got x1 by operating matrix D on it. See, x1 is nothing but D into not D into x, operating matrix D on x. What is x2 obtaining operating matrix C on x1? This we will substitute over here. So x1 is operating matrix D on x. We got finally B, C, D. So the product of these matrices is named as matrix A. Matrix A is nothing but product of these three matrices. But these are transformation matrix. So the collective transformation of all the three matrices would be matrix A. That is this when I will multiply all the three matrices, I will get a matrix A, which would be actually the transformation matrix which they are asking in the question, which is required for the transformation of the like orientation of the rigid body along. Matlab, we have to align the space coordinates with the uh, body axis of the rigid body. So this A, how will we obtain this A? Multiply this matrix P, C, D. Again, see, C phi means cosine of phi, sine of phi. It is shortcut. So when we multiply all the three matrices, we will get this kind of matrix. When you will solve by yourself, you will find that this thing is really easy. So matrix A is nothing but this matrix, and this is the required matrix of transformation in Eulerian angle determined by orientation of rigid body. And this matrix is orthogonal. Okay, what is orthogonal matrix? A into A transpose equals to I, and A transpose into A is equal to I. So yeah, this is the required matrix. I hope I am clear. Now in next lecture we will see what is conjugate matrix, trace of all this is basic. But yeah, we will see in the next lecture. Thank you.